let's work on Leetcode 1240. This question is very interesting, and this question is tiling a rectangle with fewest squares. So the question asks that given a rectangle of size n by m, and we will need to tile this rectangle by square, and we need to return what is the minimum number of square we can use to cover this rectangle. So this problem looks very horrible at first because these are okay because if everything is like this, we can use dynamic programming to solve, right? However, if you look at this example, yeah, it's not either vertically or horizontally aligned. So how to solve it? So actually, if you look at the constraints, uh, it's more clear that they want us to use an exhaustive search method to solve this problem. So what our thinking is whether we can use uh, like recursion to solve this problem. The answer is yes. So let's see how to do it. So suppose we have uh, this rectangle, right? Then we want to cover this rectangle with some square. So the way we cover is, for example, all kinds of ways. So we can do this, do this, do this, do this, in all kinds of ways. So in order to search all the combinations, the most important thing is the order. So the most important thing is the order. So we need to define the order for the search. So what is the order for the search? Here we can provide one of the choices. So here the order is first we go from left, we go from up. So we first go from left to right for each line, right? We vertically traverse this area. We first see let's see, we go this direction, right? And we try to find the first uh, the first position that is not being occupied by the square. So in this case, in the first line, we face this area is not covered by the square. Okay, and for example, if you have another case, the square is like this, and for example, this top part is already covered by some square, right? Then you still do this line search. You first see the first line, it's all occupied by square. Then you see the second line, maybe it's still occupied. Then you go at the third line. Then you arrive here. Then this is the position you want to search next. Okay, so the order is we go from top line to bottom line, and for each line search for the first position which is not covered by a square. Okay, using this order, the recursion will be simpler, and we can just follow this order to cover all the to iterate all the possible rectangle squares to cover this rectangle. And we should notice several small items here. So the first thing is, for example, you are located at this position, then how to determine the size of the square you can use. The way to do it is you starting from this position, you first go horizontally, then you reach somewhere which is covered by another square. Then you can calculate the distance from this part to your starting point. Then you have one length. Then from this part you go vertically. Then you either hit the boundary or hit another square, for example. Then the maximum square you can choose is the max of these two, which is this size. Then you can iterate all the different sizes with size less than the maximum. For example, you can either this one, and you can use this one, etc. And then we have two optimization to save time. Then we have two optimization to save time. The first is optimal solution early return. So which means whenever we see that the current count of squares we have already used is larger than the solution we have previously found, we just return early, right? The other optimization is when we search, we use larger squares first. This is the second optimization. For example, if we have this size 2 and size 1, both are valid squares we could use, then we first use size 2, then we use size 1. So in this way we can reach the first optimization early, so the total time will be reduced. Okay. Given that, we can write the code now. So we need to have a vector to remember which grid is already covered. So f equals to vector of vector size n, then vector size m. They are initially 0, and then we can put n and m here. Okay, and change those two to n and m. Okay. Then we define the answer. We initiate the answer to be n by m. So that is the extreme case. We cover all. We use all 1 by 1 to cover the whole rectangle, right? So then we do a DFS and return the answer. And we take one parameter is how many squares we have already used. So DFS, it has one parameter. CNT is the how many squares we have already used. So if CNT is larger or equal to answer, we can early return. This is the first optimization. And then we just search the first position which is not covered by the square. So we loop from I equals 0, I less than n, and for j equals 0, j less than m, j. So if Fij is 1, then we will just continue. Otherwise, we do something, then we return at the end. Okay? So this is the recursion part between this region. And after the for loop, what shall we do? We will if we can reach here, which means we never return inside, which means all the Fij are 1. So this means the answer can be equal to the minimum of answer and C and T, right? Then we just return. Because there are no return value, we just leave it here. Then we will do the actual recursion part. For the recursion part, the first step is to determine max size of square. So we call this square length by length. Then the initial value of length is max n and m, right? Then we first try to determine horizontally, vertically, how far we can go. So while I plus t minus 1 less than n, and f I plus t minus I minus 1 and j. If this is 0, then it means we can add 1 to j, to t, right? Then the length will be the minimum of length and t minus 1, right? T minus 1, because at this length, this situation is not valid, so it's t minus 1. Then we reset t and calculate horizontally. This is j plus t minus 1 should be less than m, and fi j plus t minus 1 equal to 0, t plus plus. Then length equals to length and t minus 1. Okay, now length is the maximum size of square we can use. Then remember, we will go from the maximum to the smallest. The smallest size is always 1, right? Then we can just while length larger than 0, do something, then decrease length by 1, right? And what shall we do? We cover the rectangular. What do we mean by cover? It is just set all the position to 1 in F. So we use K equals I, and K should be less than I plus length, right? And K plus plus. And we cannot use J. For example, we use L. L equals to J, then L less than J plus length, and increase L. We've put F, K, L to 1. Then of course, after we done this, we need to remove all the squares we have used. So this is just to put it to 0. Then we do DFS in the middle. And I think that's it. So let's try. After this, because for each DFS, we just do once, right? Do for this IJ position only. We don't need to do others because the order doesn't matter. If you do for others, then you are counting for different orders, then it will increase the total amount of time. So let's try. Run this. And there's something wrong here. Oh, we forgot to put it in. Yeah. So let's try. Runtime error. I think, let's see. F is predetermined. Oh yeah, remember N and M are not assigned value, so we need to change it here. Yeah, I think the answer seems correct. Let's submit. Okay, and I think that's it for this question. This question looks horrible because it's really hard to think of how to cover this rectangle for example 3. but this is actually an exhaustive search, and if you do some optimization, it won't take too long time. Let's try actually if we do not have this if, what will happen? Yeah, it will have time limit exceeded, right? So how about this? If we change the order of the search, for example, we search from the smallest to the longest. For p equals 1 and p less equals to length plus p. Let's see how things going. 31. Do this, and this will be p, right? And this is also p, and also p. So now we are delete this line. Now we are doing the DFS from the smallest square to the largest square. We expect the time consuming will be large, but we don't know whether it will. Yeah, it seems the runtime is larger, right? This will cost 101 millisecond. If you do it this way, the time will be much less, right? So, which means our two optimizations are both very important. Okay, I think that's all for this question, and thank you for watching. See you next time.